Hello everyone, welcome back to the channel. So, if you remembered, before the May-June series exam started, I was discussing about simple harmonic motions, their equations, graphs, acceleration, velocity, so on and so forth. And when the exam started, I dive more into solving past year papers, right? So now that the May-June series has come to an end, we're going to do something interesting today, which is deriving the velocity function with respect to x for simple harmonic motion. And just for you to note, this is not part of the syllabus. I mean, deriving this velocity function is not part of the syllabus, but you have to know what the function is. But to derive it is not really necessary because it's not part of the syllabus. But this is if you are curious to know where the equation comes from, then this is really going to be a very interesting one. So what are the prerequisites for, like maths part that you need to know when deriving this? You just have to know your pure maths 3 differential equation chapter. So as long as you know how to do that, and you are good to go for this. So without further ado, let's get started. Okay, so if you're thinking, what velocity function am I talking about, right? You might have forgotten, or you're just not sure what am I even talking about. So the velocity function I'm talking about is this. Velocity equals to omega plus minus omega sed, or you can just call it square root a square minus x square, where your a is the amplitude, x is any position within the motion of the spring or pendulum, anything. Yep. So now we're going to learn how to derive this equation. Okay, so let's get started. Okay. Now, so we know that the basic idea of simple harmonic motion is net force. Wait, let me write my summation properly. Net force is equals to the restoring force of the spring, to make it more specific. So if you're wondering what does this mean, I've actually explained this in the first video of simple harmonic motion in episode 1. Yeah. So because the only force acting in the direction of motion is the spring force, so therefore we say the net force is equals to the restoring force of the spring. So we know net force is ma, and we know the restoring force is negative kx. Okay, so let's make acceleration as a subject, and you'll have negative k over mx. So we have also derived this equation, and we have also come to a conclusion that k over m, okay, that is a really thick marker. Let me make it smaller. Is omega square. I've also derived this, and you will get acceleration equals to negative omega square x. This is a very famous equation in simple harmonic motion. So now, let's change this a bit in differential equation form. So we know acceleration is dv dt, right? So equals to negative omega square x. So we can actually further break this down into dv dx times dx dt equals to negative omega square x. Right, because differentiation, this particular thing is not really seen as a fraction, but if you look at it that way, when you cancel these two out, you'll get back dv dt. Right, okay. So dv dt, sorry, not dv dt, dx dt, the one I just boxed now, is your velocity, right? Because if dv dt is acceleration, dx dt should be your velocity. So if you're confused and you don't get what am I even speaking, so we have x displacement, v velocity, a acceleration. Differentiate x, you're going to get velocity. Differentiate velocity, you get acceleration. You integrate your acceleration equation, you're going to get velocity. Integrate your velocity equation, you're going to get back your displacement equation, which is your x equation. So now dx dt is this. You differentiate your x, you're going to get your velocity. So this is your v. So if we rewrite this, you'll get dv dx multiplied by v equals to negative omega square x. Okay. So now what we can do, we can actually arrange your variables. So let's put v to one side and x to one side. So you'll get dv dv, then you bring your dx to the other side, negative omega square x dx. So left hand side is with respect to v, right hand side of the equation is with respect to x. This one is a constant, okay? So we can ignore that because it's just a constant. As long as right hand side respect to x, left hand side respect to v. Okay, now what you do is you integrate both sides. Okay, so what happens when you integrate both sides now? You'll get v square over 2 equals to negative omega square. Negative omega square is a constant, so you can just ignore it like I said. But you have to integrate your x, which is x square over 2. I'm just going to put a bracket here, and plus c. You can either plus c, which is your arbitrary constant. You can either plus it on your right or on your left. I'm just used to doing it on my right, so I'm going to plus it on my right. Don't plus both sides, okay? Plus either one side. You know you won't get the answer. It's wrong. Okay, plus c. So just also to let you know, another better way to write this is perhaps negative omega square integrate x dx. This is, I think, more professional way to write, because this is a constant. You don't have to integrate that, but you need to integrate not x dx, only the x. So it's what you get, x squared divided by 2. Okay, so this is where we put in our conditions, because now we are actually very near to finding the equation for velocity. So what I mean by condition, the condition is like, I've seen this before. When x is equals to the amplitude, your velocity is 0. So if you recall back, when the motion of the simple harmonic motion, let's say a spring, when the spring is at the highest amplitude, which is basically maximum amplitude, your velocity is 0. When the spring is at its equilibrium, your velocity is at maximum. So, for example, this is equilibrium. This is when it's at maximum amplitude. This is a minimum. But still, both, okay, they don't look like they have the same distance. Let me draw a bit the same. Okay, this is the minimum amplitude. So at equilibrium, because you are not moving, you are just there, your acceleration is 0, but your velocity is at its maximum. Whereas when you are at the amplitude, whether it's the highest amplitude or the lowest amplitude, your velocity is 0, but your acceleration is maximum, because the spring, the load, is further away from its equilibrium. So it needs a lot of acceleration to accelerate back to its equilibrium position. Same thing, at this minimum amplitude, your velocity is 0 and your acceleration is maximum. So if you want more further explanation on this, you can watch the previous episode. I will actually link it in the description if you want further explanation on this. Okay? Alright. Okay, now moving on. So we have come to a fact that when the x is at its amplitude, your velocity is 0. Okay, so now what do we do? When you have conditions, you can sub in into your equation. So when you sub in, what will you get? So v square over 2 equals to, okay wait, your v is 0. So this whole thing is 0 already. This whole thing is 0. Negative omega square. Your x square is now a square because x is a, divided by 2 plus c. So to find c, your c is basically, there's no negative, it's just omega square because you bring here to the left hand side, negative is gone, a square over 2. So this is your c. So now if we were to rewrite the equation, okay, let's use a different color instead. Rewrite the equation, you will get v square over 2 equals to negative omega square x square. Okay, I think I'm just going to write it together. X square over 2 plus omega square a square over 2. So I hope you can see what I'm seeing. There is 2, oopsie, there is 2 everywhere. So what we can do is, you'll get v square equals to negative omega square x square plus omega square a square. This is what you'll get. So if you're wondering how did I even came to this conclusion, so let me do it for you separately here. V square equals to negative omega square x square divide 2 plus omega square. Okay, let's combine both this because you have the same denominator, right? So let's combine this both. Plus omega square a square divided by 2 multiplied by 2. This 2 goes over here, is going to multiply. These 2 can cancel out and this is what you'll get. Okay. Now you're actually really close to the answer. So we have v square equals to negative omega square x square plus omega square a square. So we have a very common term here, both common term. So let's v square equals to omega square a square minus x square. So I put the positive value in front, and I put a negative x square later on. So then we have this. So what can we do now? We can bring the square. So when you bring the square to the right, mathematically you're going to get a square root. But not just square root, you're going to get plus minus. So v is equivalent to plus minus square root omega square a square minus x square. Then this one can be simplified further. Square root of something squared is going to get back the value. So in this case, you're going to get back omega. So you'll get plus minus omega square root a square minus x square. And this is your final answer. Did we get back? Yep, we got back this. So that is basically how you derive the function. So if you realize, it's actually a very simple way to derive the function. Yep. So that's about it for today's video. It's very interesting, right? And it's also very easy if you know how to compute differential equations, and you'll be able to derive this function. And that's all for today's video. I hope this helps you a bit. Bye bye, and I'll see you in the next one.